So we're going to talk now about how to apply mutable state in modern Java programs in the context of case study ex3. This case study will show how to combine object-oriented and functional programming in a parallel program that uses shared mutable state. And it will do this by composing a pipeline of functions that check a list of positive odd random numbers in parallel to determine which ones are prime and which ones aren't prime. The secret sauce behind all this is something called a memoizer, which is mutable state that's shared between multiple threads in a parallel stream, as we discussed in the previous lesson. And the memoizer itself is implemented using a concurrent hash map that supports full concurrency of gets and high expected concurrency for puts. And this case study therefore demonstrates how shared mutable state can be used to optimize performance in concurrent programs. And the code that we're going to look at is available in the ex3 project in the FP folder in my Modern Java GitHub repository. So we're now back in the IntelliJ project for case study ex3. We've already looked at memoizer, so let's go ahead and look at the implementation of the ex3 case study. This particular case study demonstrates the benefits of combining object-oriented and functional programming in modern Java. It uses the Java Parallel Streams framework to compose a pipeline of functions, basically aggregate operations from the Java Streams environment, that check S-max count positive odd random numbers in parallel to determine which ones are prime and which ones aren't. It also uses the object-oriented memoizer cache that we just reviewed to optimize performance by returning results from previous duplicate primality checks rather than recomputing them once again. Although this cache is mutable shared state that's shared between multiple threads, it works correctly and efficiently since the Java concurrent hash map concurrent collection is used in the memoizer implementation. This example also demonstrates the use of the Java record type to store immutable data fields, once again demonstrating how we can combine object-oriented and functional programming concepts and features. So let's start by taking a look at the fields that exist in the ex3 class. The first field, S-max count, is a static final int that keeps track of the number of positive odd random numbers to check for primality. And we set that to a very large value, which is 2 million. The second field is called S-non-duplicate count. And this records the number of calls to the isPrime method, which will then demonstrate the benefits of using our memoizer cache. We make this an atomic integer. We have another field called S-prime count, which is also an atomic integer, and this records the total count of prime numbers found during the checks. We also have another field called S-random numbers, which is a list of S-max count odd random numbers. And let's take a look and see how those numbers are generated. So here's the generate odd random numbers factory method. It returns a list of count odd random numbers that will most likely contain duplicates. As you can see, it takes a random number generator here as the first parameter and the count as the second parameter. And then it goes ahead and makes use of a Java stream, which will generate an infinite stream of random positive ints within a range designed to ensure duplicates. You can see here that the range goes from the maximum integer value minus count up to max value. So we're very likely to get lots of duplicates here. We then use the filter operation from the Java Streams framework to eliminate even numbers. And let's see how we do that. You'll see we pass in a method reference to the isOdd predicate method. And this predicate method returns true if the integer parameter passed to it is an odd number, otherwise it returns false. You can see the way it does this is it uses the bitwise AND operator, which returns true if the integer is odd and false otherwise. And it does that by taking the integer parameter and ANDing it by the value 1. And if that returns 1, then we know it was odd, otherwise it's even. So we use isOdd here in conjunction with filter to get rid of the even numbers. We then use the limit short-circuiting intermediate operation from streams to limit ourselves to count odd random numbers. We then convert that stream of int primitives into a stream of integers by using the box method. And then finally, we use the toList terminal operation to trigger all the intermediate operations and collect the results into a list. So that's where we get our list of odd random numbers. The next field in the class is called S-memoizer, and this is an instance of our memoizing cache that we'll use to demonstrate how shared mutable state can optimize the performance of a concurrent Java program. And you can see here that we pass the isPrime method reference to the constructor of memoizer. Let's go take a look at isPrime. The isPrime method is used to determine whether a parameter called prime candidate is prime, and it returns the result. It'll return 0 if the prime candidate is prime, or will return the smallest factor if the prime candidate is not prime. So let's take a look at the implementation of isPrime. The very first thing we do here is really just for statistic bookkeeping purposes. We increment the count of non-duplicates, which means these were integers that were not found in the memoizer cache. And we're going to do this to demonstrate the benefits of using a memoizer cache. The next thing we do, which actually gets into the isPrime algorithm, is we check to see if the prime candidate is a multiple of 2. So if the parameter, when modded by 2, returns 0, that means it can be evenly divided by 2, which means it's an even number, which means it couldn't possibly be a prime number. So in that case, we return the smallest factor, which is the value 2. If the number is not an even number, then we go ahead and just check the odd values for primality. And here's the way this works. We start out by setting a loop counter variable called factor to 3, and you can see that we skip over even numbers. So we'll go 3, 5, 7, 9, 11, and so on. The loop condition multiplies factor by itself and checks to see whether or not it's less than or equal to the prime candidate. Recall that a prime number is a number that is not the product of 2 smaller natural numbers. Assuming we make it through the loop condition, we then check to see whether modding the prime candidate parameter by the factor returns 0. If it returns 0, that means prime candidate was not prime, so we return factor as the smallest factor. If we make it all the way through the loop, we then go ahead and return the value 0, which indicates that the prime candidate was indeed prime. There are just a couple more fields we're going to take a look at before we dive into the actual method implementations. The first field is called sMemoized, and it's a function that uses the memoizer to check an integer for primality. And the way it does that is it's going to end up calling the checkIfPrime method, which we'll look at shortly, passing in the prime candidate and the instance to the memoizer. There's also another field called sNotMemoized, which will check an integer for primality without using a memoizer. As you can see here, it calls the checkIfPrime method, passing in the prime candidate, but passing in null for the memoizer, which means don't do memoization. And we'll take a look at the implementation of checkIfPrime momentarily. Let's now take a look at the main entry point into this test program. We parse the command line arguments first, so we can do things like set whether we're using debugging. And then we go ahead and we warm up the cache. And the reason that we warm up the cache here is to ensure that the threads in the common fork join pool are initialized, thereby ensuring that we don't count the time required for initialization against the time when we record the computations to check whether something is prime later. This particular call does not record the time taken to perform the computations. Once the thread pool has been warmed up, once we've warmed up the common fork join pool, we're then going to do a number of timed tests. These timed tests will use the time run method on the runTimer helper class. We've looked at this before. It basically keeps track of the start time and the end time, and it stores the execution time in an internal map using the string as the key that keeps track of the time needed to execute the particular runnable that's passed in here. In this case, we're passing a runnable in that we'll call the checkForPrimes method. The first, called the checkForPrimes, doesn't use a memoizer to check odd random numbers in parallel to determine which are prime and which are not. We then go ahead and print the statistics for the non-memoized version, and then we make 2 calls to checkForPrimes, passing in the memoize function. And we do this twice because the first time we do it, we're going to demonstrate the use of an empty memoizer. And when it runs, it's going to put items in the cache. And we'll see what the benefits are in terms of performance by caching the items in this shared mutable state. Then, just for kicks, we run this test once again, and this time the cache will be completely full, and so all the checks that are run, we run entirely out of the cache. There'll be no computations of the isPrime call at all. When we're all done with this, we print out the timing results, and you get to see which of these different methods work the best and how much they differed. Let's now take a look at the implementation of the checkForPrimes method. This method checks a list of positive odd random numbers in parallel, and then it uses that to print and determine which are prime and which ones aren't. So it takes in the list of random numbers, and it takes in this prime checker function, which either uses the memoizer or it doesn't. The very first thing we do in checkForPrimes is we set some counters back to their initial state so we can keep track of the number of non-duplicates and the number of prime numbers we encounter. Then we convert the random numbers list into a parallel stream, so all the computations that check for primality will run in parallel. And then we use the map intermediate operation to call the prime checker function to check each number to see if it's prime. And we'll take a look at the prime checker function in just a moment. And the final thing we do in this stream is we use the for each terminal operation to trigger all the intermediate operations and then handle the results by printing them out. Here's the implementation of checkIfPrime. This is the method that gets called in the stream in parallel to determine whether its parameter, prime candidate, is prime or not. And you can see it takes the parameter and it also takes a memoizer. And that memoizer is going to be used to demonstrate the benefits of shared mutable state in a concurrent program. The checkIfPrime method creates a new prime result record. A record is a data type that was added in Java 16, and it holds plain old data, or pods, that keep track of the result of a primality check. Unlike a traditional Java object, a Java record contains no hidden fields. There's no virtual pointer or v-pointer, there's no virtual methods, there's no intrinsic lock, there's no intrinsic condition, it just stores the data. It's a bit like a struct in the language C. And the two fields that are part of the prime result will be the prime candidate, which is the value we're evaluating for primality, and the smallest factor, which stores the result of calling the isPrime method on the prime candidate. The prime result is initialized in checkIfPrime by passing in the prime candidate, of course, so we can keep track of that value. And then we're going to pass in the result of either calling Memoizer's get method on the prime candidate to get the result from the Memoizer, which may accelerate primality determination if that value was previously cached, or if the Memoizer parameter is null, we're going to call the isPrime method directly. So in that case, we bypass the cache, and we just call the isPrime method each time. As you might expect, not using the cache will have a negative impact on performance if there are lots of duplicate values in the list of odd random numbers that we're checking for primality. So now that we've walked through the implementation of this particular case study, let's run it and see what the results look like. As you can see, we're testing the primality for 2 million numbers, and as it runs, it prints the statistics. As you can see here, there were roughly 185,854 prime numbers in that list of 2 million numbers. When we didn't use the Memoizer, there were 2 million calls to isPrime. When we used the Memoizer the first time, you can see there were many fewer calls to the isPrime method, basically only 864,813. So that means there were over 10 million calls that were actually fielded by the cache, by that shared mutable state in the Memoizer. And then when we ran this test again with a fully initialized Memoizer, there were 0 calls to the isPrime method. And here are the results printed from fastest to slowest. You can see that when we didn't memoize anything at all, it took about 3,023 milliseconds. When we used the Memoizer the first time, it was nearly twice as fast, indicating the benefits of using a Memoizer. And then finally, when we used the Memoizer where everything was in the cache, it was incredibly fast because there were no calls to the isPrime method whatsoever. So this example demonstrates that by using memoization and shared mutable state in modern Java, you can get substantial increases in performance. Naturally, the Memoizer implementation we used was carefully designed to leverage the concurrent hash map, thereby ensuring there were no race conditions, as well as also ensuring that the performance was optimized because concurrent hash map is designed to allow full concurrency of reads and very high concurrency for writes, where reads are implemented by the get method and writes are implemented by the put method. That's the end of this lesson that talked about how you can apply mutable state in modern Java programs by leveraging techniques such as memoization and Java's concurrent hash map.